All right, ladies and gentlemen, good afternoon. Welcome to Fighting for Five, episode 17, where we go over the document number 18. And of course, brought to you by Couch Potato Brand Snack Foods and Beverages. All is going well in the world of Couch Potato Brands. All right. So this is the farewell to the document, and it's a sad day, but it's also a proud day as we now move on to the next chapter of our prep for the AP exam. And that is starting tomorrow, really we're just going to focus on what a lot of the predictions are for the 2020 exam. All right, so anyway, let's do this problem. Part A. Anyway, we're given a situation and we're asked to, in part A, to construct a confidence interval to basically estimate the true proportion of adults in the United States who would have chosen the quote unquote economy statement. All right, so now, of course, whenever we're building a confidence interval, we center it around the sample statistic, which is in this case 0.37, that's your p hat, and then we add and subtract the margin of error. But of course, you should define your parameter. In this case, there's only one p, call it the true proportion of all US adults who choose the economy statement. We're going to run a one proportion z interval. Like I said, p hat was 0.37, sample size was 1048, and of course, this is a 95% confidence level, as we were told to use. As far as the justification, no need to, because we're told that all conditions are met. And since all conditions are met, this means that p hats are going to be distributed normally, centered at p, which is unknown, so I'm going to leave it as the letter p as a placeholder. And the standard error will be radical pq over n. The thing is, again, I don't know p, so I need to approximate p, and the best approximation we have is p hat. So that's why you see p hat q hat over n. And our standard error is approximately 0.0149. And so our 95% confidence interval is just 0.37 plus or minus z star times 0.0149. Z star in this case is 1.96. You find that using inverse norm 0.975. And your confidence interval ends up being 0.3408 and 0.3992. Now to interpret, so that's your confidence interval, let's interpret what it means. It means that we are 95% confident that the true proportion of US adults who would have chosen the economy statement is between 0.3408 and 0.3992. There you have it, that's part A. Now part B is very interesting for a couple of reasons. One of them, really the main reason is I feel like this is definitely a type of question that you could potentially see on the exam this month, where they ask you to tell why do we check a certain condition. So in this case, they're asking you, why is it that we need to check the success failure condition? And in order to answer that question, I want to remind you about the relationship between p hat and some x, where x is binomial and p. Now, if you think about it, p hat, when we calculate p hat, we are calculating the number of successes and we're dividing by the sample size, right? Now, the number of successes, hopefully you realize, is actually exactly what a binomial random variable counts. It counts the number of successes in a certain given number of trials. Okay? You might also recall that we said that as long as certain conditions are met, if x is binomial and p, then that same random variable could be modeled using the normal distribution with a center of NP and a standard deviation of radical NPQ. Now, take a look. See how this relates to P hat. Remember, if certain conditions are met, P hat can be distributed normally with a center of P. Notice that in order to get from NP to P, all you must do is divide by N. Similarly, the standard error of P hat is radical PQ over N. Notice that in order to get from radical NPQ to radical PQ over N, you just must divide by N. So really, whenever we study P hat, all we're doing is we're taking a binomial random variable and we're transforming it. In other words, we're taking all the possible data points, and we're dividing them by N. So the binomial distribution is very closely related to P hat. Now let's go back to the binomial distribution. In class, I showed you this Excel spreadsheet. This is an Excel spreadsheet of a binomial random variable. In this case, the binomial random variable, there are 40 trials, independent trials, and I said that the probability of success is 0.5. If that's the case, then our binomial random variable looks like, where'd it go? It looks like it disappeared. Oh, there it is. So if that situation, as mentioned above, is the case, then it looks like our binomial random variable has a distribution that looks like this. And what you'll notice is that even though this is a discrete distribution, it looks like I can fit a normal curve to approximate this discrete distribution. All right. And in this situation, n times p is greater than 10, and n times q is greater than 10. Now let's see what happens when I adjust the probability of success to be, let's say, 0.05. All right, so in this situation, n times p would be less than 10. So this would be a situation where the condition is not met, and here's why that's a problem. Notice that the distribution, the binomial distribution, what has happened is that it kind of shifted to the left. And in fact, it shifted a little too far to the left, where if we tried to fit a normal curve to this, there would be way too much area in the negative values of the horizontal axis. And since realistically, a binomial random variable cannot be negative because we're counting the number of successes, this would be a situation where we would not want to model the binomial random variable using the normal curve. Right? So when n times p is not greater than 10, we have a situation where there's too much area in the negative sense. Let's see the other extreme. Let's say the probability of success was very large. Hopefully you can sort of predict what will happen. So if the probability of success is very large, we have the opposite problem, and that is now the entire probability distribution shifts way to the right, and there's too much area. If we were to try to fit a normal curve to this, there's too much area in the values that are greater than 40. And if there are 40 trials, then there can be at most 40 successes, of course. And so this is a problem. So if n times q, which is the situation here, if n times q is not greater than or equal to 10, then we have a curve that has too much area in values that are too high, that are not possible in the high sense. All right. So basically, the bottom line is what I'm trying to tell you is that the reason we need n times p and n times q to be greater than or equal to 10. And notice that p and q don't have to be 50-50. I chose here now 60-40. You'll see that, yes, there's still a slight shift towards the right, but it's not shifted far enough where there's a lot of area in the values above 40. And it's not shifted far enough to the left where there's a lot of area below in the negative numbers. So the bottom line is We need that success failure condition to be met so that we can fit a normal model to our distributions, our distribution of p hats. The distribution of p hat would look exactly like this binomial distribution, except instead of 0 through 40, you'd have 0 over 40, 1 over 40, 2 over 40, all the way up through 40 over 40, right? The proportions will range from 0 to 1. The shape would be exactly the same, though. Anyway, long story short, the bottom line is, to answer part B, we would say that the success failure condition allows us, or let's say is required to guarantee that we can use a normal model to approximate the sampling distribution of p hat. Okay, there you have it. That would be the answer that you want to give. And let's check out part C. Part C says that a suggestion was made to use a two-sample z interval for a difference between proportions to investigate whether the difference in proportions between adults in the US who would have chosen the environment statement and adults who would have chosen the economy statement is statistically significant. Is a two-sample z interval for difference between proportions appropriate in this case? Now, a couple of things. Since this question is asking, when reading this, you might think to yourself, this sounds like a hypothesis test, a job for a hypothesis test. And you're absolutely right. We are looking to see if there is a difference between these two population proportions. So really we're asking the question, is the difference in these proportions statistically significant? And typically, if you're left on your own, you would, without a doubt, go ahead and use a hypothesis test. But in this particular case, with this type of question, the hypothesis test, your null hypothesis would be maybe that like P1 minus P2 is equal to 0, of course. But the alternative hypothesis would be P1 minus P2 is not equal to 0, right? Because the question is not saying, is one greater than the other? It's just saying, is there a difference in these proportions? Are they different at all? And so the fact that this question is asking a two-tailed test means we can actually answer it in two ways. We can answer it using a hypothesis test, just the standard way that we normally do, but equivalently, we can go ahead and use a confidence interval, believe it or not. So this, and I believe I made a video discussing this, and this information is available in the textbook, but there is a relationship say it this way. Confidence intervals and two-tail hypothesis tests are logically equivalent. In other words, I'm not saying that let's just say hypothetically, let's say we're trying to see if there's a difference between two proportions, and I end up building a confidence interval and I get 0.1 to 0.6. In this situation, we would say that it is feasible that there is in fact a difference between the two proportions because 0 does not exist within this interval. On the other hand, if we were building a confidence interval for the difference between two population proportions and we got like negative 0.1 to positive 0.1, then we would say that this is actually evidence to suggest that there is no difference because of the fact that 0 exists, right? So in this one, you might reject H null. Remember, H null being that they are equal to 0. The difference is equal to 0, I should say. Whereas this one, it would be logically equivalent to fail to reject H null. So that being said, even though this does sound like a hypothesis test type problem, and you'd be totally fine to attempt a hypothesis test, realistically, it is okay to run a confidence interval in a two-tail situation. They are logically equivalent. Now, all that being said, either way, you should not build a confidence interval because the two populations that you're studying are dependent on one another. So really, long story short, ignoring everything I just said, the answer is no. Let me go back and just reread the question. So the question really is a two-sample Z interval for difference between proportions an appropriate procedure? No. A two-sample Z interval is not an appropriate procedure because the parameters are dependent on each other. In other words, we don't have two independent populations that we're surveying. So if in this sample, if one person says economy statement, well, that's one fewer person that can choose the environment statement. So these values are dependent on one another, and therefore we cannot compare them. If you look at the previous video, you'll notice that one of the conditions to run that two proportion Z test was that the populations were independent of one another. That is not the case here, and therefore we can't use any sort of two proportion Z interval or hypothesis test to answer the question that was just asked. All right, folks, that is all. I hope this helps. Let us say goodbye, but also let us say thank you to the document. And starting tomorrow, we start really focusing in on 2020. All right, take care, ladies and gentlemen. Bye.